So we are on to more trusses, more things with trusses. Well, my cursor's still working on those. I did change the quiz dates. So the quiz dates were set till, I don't know, like the 13th, and then it was due the 8 o'clock the 14th. I just switched them all to do on a Sunday, so the following Sunday. So because a lot of the online students, they can only do it on the weekend or whatever. So all the quizzes are due on Sunday now. Quiz 1's already done. So, but all the future quizzes, 2 through 5, are due on the Sunday after whatever day, or at least that's the intent. I think I set them all that way. So that'll give you a handful of days to do the quizzes more. Let's see. So we did this idea. We called it the method of joints. And what you do in the method of joints is talking about a way to solve for member forces in trusses, which is normally the first step in figuring out if this truss is going to fail or do what you want it to do. So for the method of joints, you look at each joint. So the joint is where 2 or more truss members are connected together. So you look at each joint, and you're looking at it as a concurrent force system. And normally, and all the time for this course, but outside of this course, other times it could be different, but normally they're going to be a 2D concurrent force system because we're looking at planar trusses, and we're assuming that the way they're connected together, those members don't really carry any force in them. So we're looking at like a plane of truss members. But it is possible that these concurrent force systems would be in 3D, which would work just as same as 2D, except now you have the third dimension in there to deal with. But you do this, and so it's good. This method of joints is good when you're solving for every member force in the whole truss. Because you could eventually go around to every joint, or well, you don't have to do the very last joint because you would have already solved it by then. Also, when you have symmetry in the truss, like the truss shape is symmetrical and the loading is symmetrical, then you really only have to solve for half of the truss and then mirror it over to the other half. That's only good when there's symmetry though. But so this is a good process when you want to solve for everything, or it's also good if you only want to solve for 1 or 2 things, but they're on the perimeter of the truss. How did I write this? Solving for member forces on the perimeter of the truss. So there are other methods. We're going to talk about one called the method of sections today in a little bit. But method of joints will always work. Well, it will always work for statically determinate trusses. So there is this idea of statically determinate. And statically determinate is not specific to trusses, it's just to any static thing. But what it means is that you can use the methods of statics, like summation of forces into X and Y and that kind of thing, to determine the internal forces. Maybe we'll write that down. So the statics equations like summation of forces equals 0, that kind of stuff. They statically determinate means that statics equations are sufficient to determine the internal and external forces, you know, like an external reaction at a pin or a roller, and the internal member force. All you need are these statics equations. So static equations are sufficient to determine internal member forces, or let's just say internal forces because it's not specific to trusses, and external reactions. You don't need these other types of equations that we haven't talked about. But there are trusses and other things that are statically indeterminate, which would be the opposite of this, right? So statics equations are not sufficient to determine the internal forces and or the external reactions. So you don't want to get into these statically indeterminate things. Because you could, particularly in the group project at the end of the course where you're building and designing this truss, you could certainly design one that is statically indeterminate, meaning you can't use the equations you know to solve for all the member forces. You would have to use some other equations, like maybe some kind of strength or energy or whatever. You'd have to add some other equations to it to be able to solve for the member forces. So we want to make sure that we are using statically determinate trusses. And how we might determine that is this little equation, M plus, we'll put a 3 in here. Sometimes you'll see an R, I'll define these in a minute, is less than or equal to J times 2. So M is the number of members in the truss. This is specific to trusses. 3 here is the number of external reactions, so 2 at the pin and 1 at the roller. So it's always going to be 3 for our trusses. So sometimes that'll just be an R for reactions. And then J is equal to the number of joints in the truss. And if this equation is true, if M, the number of members, plus 3, the 3 external reactions, is less than or equal to J times 2, 2 there is that you have, again, this is 2D planar trusses, so the 2 represents summation of forces in the X direction at every joint and summation of forces in the Y direction at every joint. If this equation is true, then it is statically determinate. So here, let's draw one. Here would be a truss. Maybe like this. We'll have a pin. The pins are not always on the left end and the roller always on the right. I just, all the times, draw them that way. So here is something that you might think of as a truss. Now this one has the rectangle in the middle, right? So got this rectangular shape in the middle, which is not what we normally want. Remember, we normally want all these closed loops to look like triangles, and that's definitely not a triangle. So when we solve this equation, M plus J, oops, let's not write it in the highlighter though. M plus 3 is whatever, less than, equal to, greater than J times 2. M, we have 1, 2, 3, 4, 5, 6, 7. We have 8 members. So 8 plus 3 is 11. J, we have 1, 2, 3, 4, 5, 6 members. So 6 times 2, we have 11, we have 12, so that's less than. So when this equation turns out less than means that it is statically determinate, which is, we want that. But it's unstable. So there aren't enough members in the thing. And that's kind of what we talked about when we said that this square shape in the middle is not a fixed shape. You know, when you put 4 sticks together and put them together with these pins, they will flop around into rhombus shapes and all this other stuff that's not the shape you intended. Whereas a triangle, if you put 3 sticks together in a triangular form and pin them together, it will only ever be that triangle unless you break one of the pieces. So it's statically determinate, but it's unstable, which is not what we want. So we stiffen it up and we take the same truss.
Can you explain again what statically determinate means?
It means that a statically determinate means that I can use the equations of statics, summation of forces in X, Y, and a summation of moments to solve all the member forces and reactions. And that's all it means. It means I can determine all the internal forces and reactions using statics and nothing else. I don't need other things outside of statics, like mechanics of materials or something else. basically for this course, statically determinate means I can solve the problem. So
it being unstable just means that
unstable means that if I drove a truck across it, it might like flop around, or it might not hold together as the shape that I intended for it to be. So I can still solve the problem, but it may not remain a truss. It may not, but it's not fixed in that arrangement of members. Now this particular one, what could happen might be a little bit difficult to figure out, but if I started driving a truck across here, and it ends up over here, then it's possible that this truss could not break or bend any piece, but could look something like maybe, I don't know, because I've got this roller over here, right? So that end can move left and right, and I could end up with something like, I don't know, let's see, might look kind of like, there's that piece. It could do some weird things. Well, I guess the ground would stay put. We'll assume the ground stays put. So where's the other one? It could do something like, those have to be parallel. I don't know what it would look like, but it would change shape. Basically, I'd have to actually draw it where I could animate it to figure it out. But basically, this piece in here could potentially become a rhombus. Now, in this case, I don't know that it actually would, because we were supporting it with the ground over here. And so I don't think it can move around, but it's not for sure going to stay looking like the bridge thing that I made it into. Maybe I'll animate one of these in SolidWorks, and we'll do it, not in class, but I'll draw one up so that we can watch how it could move around. But to make it statically determinate and stable, then normally I would maybe put an extra member in here. So now all of my little shapes, they're all triangles in here. And when I solve my equation, m plus 3j times 2, I've added one member, so I have 9 plus 3 external reactions, and it's going to be equal to, I still have the same number of joints. I didn't add any joints, I just added one member in there, 6 times 2, so that says 12 equals 12. And whenever this little equation is equal, so equal means that it is still statically determinate, meaning that I can actually solve for all the member forces using statics. And it's stable, meaning that I don't have to think about how this truss might change the orientation of the members relative to one another, because they can't. They're all triangular shapes, so they're all triangulated. Now I could say that, well, that was good, let's add more members. And so here's where I'm at, and let's add one across here. And I'm saying that there's not a joint right here. These kind of overlap in the middle. So I didn't add a joint, I just kind of crisscrossed these members here and added another member. So when I do that, then I have 10 members, so I'm doing m plus 3. I want to know if it's greater than, equal to, or less than j times 2. I have 10 members now, still have the 3 external reactions, and that's going to be greater than, I have not added any joints, so 6 times 2. So I've got 13 is greater than 12. And when this equation flips to greater than, then it is statically indeterminate, meaning that if I did the method of joints and tried to solve for all the member forces, I wouldn't be able to with the things that I know from statics. So it's statically, oops, I wrote determinate, it's indeterminate. So indeterminate, but it is stable. you know, I've actually added even more pieces to it. But I wouldn't be able to use summation of forces in the X, Y, Z, and summation of moments to solve for all these member forces. One of them would get left out. Basically, I have too many unknowns for the number of equations I can generate with just statics. I have to go and figure out some other kind of deflection equation or something to add to this to make sure that I could solve for everything, which means that I have to use something outside of statics to solve for. I can still solve for them all, just not using statics. This also can happen if you use two pins. So instead of the pin and the roller as the support, then you have two pins, and that 3 in my equation now becomes 4 because each of the two pins has 2 reactions instead of 2 reactions at a pin, 1 reaction at a roller. And that can also make the equation flip over to statically indeterminate. And it doesn't mean you can't solve for anything. You know, there are ways that you might can solve for a couple of the member forces, but you won't be able to solve for all of them. So that is a thing. We want our trusses to end up in this statically determinate, so everything's a triangle, and stable, so that I have enough members in there that it doesn't have the risk of, well, not deforming. I don't want to say deforming because that means changing length or shape or something, but keeping everything, all the members the same shape, but not holding their geometric shape that I intended, like that square in there, which is not what I would want to happen.
So adding that extra member, like would that,
Adding that extra member, the red one?
would that like be, I don't want to say, like if like a bunch of trucks or something, like what would be the problem with doing that in a real like situation?
There's no problem. The problem is just that right now we only know statics, or we're learning only statics, and we couldn't solve for all the forces, so we couldn't figure out, oh, there's going to be 5 kips of tensile force in that red member, I need to make it this big. So that's the only problem. In the real world, it's fine because I know other methods to solve for these things. So practically, there's no problem with it. For the methods that we are going to learn in this class, the problem is I wouldn't be able to solve for everything. So it is not a problem to add more pieces. It's just that I won't be able to solve for all the forces. If I did put a joint here, then I might be okay because I've added a joint and I would have a 7 instead of a 6. So 7 times 2 is 14. And I've still got the 10 plus 3. So it would actually make it back on the statically determinate side, but not necessarily, it may not be stable. But stable here, it doesn't mean the truss is necessarily going to fall down. It just means that I am assured that it's going to be stable when it's equal like this and statically determinate. So it's kind of, we're limiting things based on the content of the course versus what might happen in reality or whatever. I don't know if there's an idea of more stable. It's more is if there's a unique solution or not might be a better way to think of it. Versus stable as far as falling down.
Could you say there's a better way of doing it then, instead of saying more stable? Like one bridge would be, one like design of a bridge would be better than the other, even if they're both stable?
Oh, sure. That could be true, because you would have the idea that, well, you have to define what better means. Does better mean stronger, cheaper, easier to build? You know, there's lots of definitions of better. And so then you're thinking of design type equations or design goals. And for me, it might be that, well, I got to build this bridge as cheap as possible. And somebody else, it might be, I've got to build it as fast as possible. And somebody else, I've got to build it as strong as possible. And so you have all these competing things that make it difficult. And that's kind of what, in general, not just to trusses, but in general, your job as engineers is going to be, is figuring out this balance between, all right, I can make it that good for that amount of money in that amount of time, but I can't make it better in less time. You have to balance out what's realistic for whoever you're building or designing this thing for. Those 3 things. How good is it going to be? How, and good might be strong or whatever. How quick can I get it done, and how much is it going to cost? Those kind of are all competing a lot of times, variables that have different weights depending on what your employer or what you are trying to accomplish. So yes, one will be better, but it depends on what you define as better. Okay. Let's look at this item. So we started out with talking about method of joints. You can use method of joints. We've used method of joints. If you've done the web work, you've done some problems with method of joints. And you can use that pretty much every time, because I'm not going to give you a problem that is statically indeterminate in the course of this class, because it would not make sense for you to do that. So you know you'll be able to do method of joints. The problem with method of joints is that depending on what I'm asking you to do, it's not the best process because it might be lengthy. Like it might take you a lot of equations to get to what I'm trying to do. If you were trying to solve for every force in the truss, every member in the truss, then my method of joints is great because it doesn't care. You want to solve for everything anyway. If you want something on the perimeter of the truss, so over here in our little trusses here, if you want to solve for member AB, method of joints is just fine. CD, also fine. DE, probably good. AF, okay. FC, to get to figuring out FC, I've got to write a method of joint at maybe D, solve for those two. See that, well, it depends on where the force is. I didn't put a force on here. Put the force over here to make it simple. See that CE is a zero force member, then go to joint C and solve for CF. So there's a lot of steps to get to this. But there's another method of sections, where I can write one free body diagram and solve for member CF. So sometimes method of sections is going to be a faster, less equations to write method for solving a particular member force. And in reality, method of sections and method of joints are really the same thing. You're isolating a piece of the truss, whether it's a joint or a section, and you're drawing the free body diagram of that thing, and you're solving your statics equations. The difference with method of sections is that I'm not looking at a single joint anymore that's a 2D concurrent force system. So when I look at a whole section of the truss, now I add in a third statics equilibrium equation. I add in the summation of moments. So the idea is that you're going to draw a free body diagram of a section instead of a joint of the truss. And then, so let me add one little thing. You probably have to solve for external reactions. So that was kind of the first step in method of joints also. It is not guaranteed that you have to do that first, but most of the time you're going to have to solve for external reactions first. In this truss that we just drew, if I want to do the method of joints at D, I need to know how much that roller at D is pushing on D, or pulling on, or whatever it's doing. So I need to solve for external reactions first a lot of times. It's not guaranteed, but if you're unsure, then the first step is usually for either one of these, method of joints or method of sections, solve for the external reactions first. Then draw a free body diagram of a section of the truss and apply summation of forces in X equals 0, summation of forces in Y equals 0. So you could do both of those for the method of joints, but when it's a section, you can also do summation of moments around some point equals 0. So you get 3 equations, meaning you can solve for 3 unknowns. A couple of things. The section must be completely separate from the rest of the truss. So you can't like leave one little piece connected and try to isolate another section. You have to cut a part of the truss completely away from the rest of the truss. Draw that free body diagram. So it's just like the idea of drawing any other free body diagram. You isolate one body. In this case, the body is going to be a collection of truss members, and you draw all the connections. In this case, the connections are going to be the truss members you had to cut to separate it. One other little detail is that you can only, and then I'm going to say cut because I mean cut when you draw a circle to isolate your free body diagram or whatever, 3 members. Because every member that you cut through to create your section is going to create a new unknown. It's going to be the force in that member that you cut apart. And you only have 3 equations, x, y, and moments. So you can only cut through 3 of them. So let's draw us a little truss of some sort. I have one here. Let's see. Let's put 3 kips up here. And oops. There'll be 2 in there, I guess. Maybe we need some more. I don't know. Every one of the little squares is 1 foot or unit or whatever we're looking at. All right. So here's something that looks like a truss, and let's say that well, at least it has. Well, let's check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 has 11 members. 1, 2, 3, 4, 5. Well, 1, 2, 3, 4, 5, 6, 7 joints. Has a pin and a roller, so that means that the reactions are 3. So M plus R is whatever compared to 2 times J. M is 11 plus 3. 2 times J is 7. So I have 14 equals 14. So it is statically determinate, and it is stable. So it doesn't have, it's not, basically it means that everything's triangulated, and I don't have too many members to solve for all the forces. So I should, if I was asked to solve for any one of these member forces or the external reactions, I should be able to solve for it using statics. All right, so let's say that the one I want to solve for is this one, B, F. So this will be A, B, C, D, E, F, and G. So I want to solve for this one, the force in that member, which I could do with method of joints, but I can do a little bit faster with method of sections. So let's see how that might work. First, either one of the sections that I'm going to draw, I'm going to need some of the reactions. So let's solve for the reactions. I don't actually need, what my plan is I'm going to cut this one open, and then I'm going to cut here and here. So I'm going to, that's my plan. I need to cut through BF because that's the one I want to solve for. And then I also am going to cut through BC and FG to make section ABG down there at the bottom with the pin and all that. So I don't really need anything on the other side. So I don't need the reaction at the roller. So since I don't need the reaction at the roller, I'm going to try and see if I even need to solve for it. But I don't know, because I don't know. Well, let's write this equation first. AX, or summation of forces in the x direction, equals 0. Remember, this is not a free body diagram that I've drawn. Here's a thing not to do. So, you know, you draw your picture of the problem statement or whatever, and you don't want to redraw it. So you go in and you like draw an arrow here and arrow here and arrow here, just to say that those are the external reactions for the pin and the roller. You probably know what you mean, but what it actually looks like is that I've got this truss, I've got a pin and a roller, and then I've got some other forces on top of the pin and the roller. So while you're solving the problem, it's probably fine, but if anyone or you look at it much later, then it's ambiguous. Are these extra forces on the pin and roller, or are those the reactions at the pin and the roller? So generally not a good idea to do it that way. For me, I can erase these, right? So I can erase these and put EY, that was a roller, and the ground that the roller, the little wheel was rolling on was horizontal, so that makes the reaction vertical. And here there was a pin, AY and AX. Now it's a free body diagram. I guess technically I need to put some kind of coordinate system just to make sure that I know which way is positive X and Y. And it's important to solve for any external reactions you want before you go cutting the truss into little pieces, because the external reactions are to the entire truss, not to a piece of the truss. So I need to look at the whole thing, get all the reactions I want, then start chopping it up into little sections or joints or whatever. So where I was going is I was writing summation of forces in X equals 0, and the only one is AX. So therefore AX is 0, so I can get rid of that one. Now if the 3 kips was at an angle other than vertical, then yes, there'd be some value for AX, but right now we're keeping it relatively simple. And if I plan on basically, you know, cutting that part out, then I only need AY. So if I do summation of forces in the y direction, I get an equation that says AY plus EY equals 3,000 pounds, which doesn't do me any good. So instead, I'm going to say summation of moments about E. So I have been doing, let's do counterclockwise positive. I have been doing summation of moments about the pin, which would be A, which is fine also, because as long as I have 3 external reactions, I can solve for all of them. But if I'm trying to save, you know, like I'm on an exam or whatever, and I'm trying to save a few seconds, then if I don't ever write that equation, and I can write the moment equation and get what I need, then it saves me a little bit of time. So if I do moments about E, that will make the force EY, the reaction at that roller, not enter into the moment equation, and I'll only solve for AY and AX, except I know that AX already is 0. So sometimes, a lot of times, it pays to spend, you know, 10 seconds or 20 seconds kind of planning out the order you're going to solve these equations in. If you're unsure and you're spending, you know, minutes trying to solve out the order, then just write all the equations and solve them, and it'll end up being faster than trying to figure out what order to do them in if it's taking minutes to do that. But if it's a few seconds, then that's okay. All right, I said counterclockwise is positive. So the 3 kips is going to be counterclockwise. 3 kips, and it has a moment arm of, oops, I wanted that to be blue. 2. We'll call those feet. I didn't actually label them, but feet. And plus or minus, because the way I drew the AY arrow would create a clockwise moment about E. And I said the counterclockwise was positive. So AY times 9 feet. And therefore, I can solve for AY. Let's see. 3 times 2 divided by 9. So AY is 0.67. My units on these are kips. Remember, that's 1,000 pounds, so 670 pounds is what it's telling me. Then I make sure, does that make sense? Kind of makes sense. Basically, I've got 3,000 pounds total I have to support between AY and EY. And this is telling me that EY is going to support most of that. But the 3,000 pounds is closest to EY, so that kind of makes sense. If I had gotten some number like AY is 6,000 pounds, but I only have to support 3,000, then maybe I have to question if that's done correctly. But this makes sense. Okay. And then I could go solve for EY if I wanted to. I could write the summation of forces in the Y direction. But again, if I only want to know the member force in BF, then I don't need EY. So I'm not going to write it. What I am going to do is I'm going to go back now, cut this section out, and draw that free body diagram. So I've got point A, or joint A, got a member that goes over here to G. Then I've got one that goes up here to B. I did not cut through any of those pieces, so they're just still members. And then I've got AX is 0. I'm not going to draw it on here. AY I found out to be 0.67 kips. And then I cut through member BC. I'm going to draw it in tension. And just as force BC, I don't know what it is. I just know it goes, I don't know that it goes that direction. I know that it's in that line of action. It may actually be pointing down towards B, meaning it's compression. So if you know that it's in compression, then you can draw it that way. Again, I'm just going to draw the unknowns in tension and let the equation tell me if it's tension or compression. But it doesn't actually matter which way you do that. BF, I'm going to draw again in tension. And then FG, I'm going to draw it in tension. So now I've got three unknowns, BC, BF, and FG. I've got a free body diagram, basically what's left of the little truss that I didn't cut through. And then I've got the reaction at A. And I've got three equations that I can use to solve for this thing. Let's put some information on our truss here about dimensions, though. Move it down a little. No. So let's see, these things have FG and BC, they have a rise of 3 and a run of 2. That gives them a little hypotenuse of square root of 12, I guess. Or square root of 13, not 12. 3.6. Yeah, we'll do 3.6. And G would be the same. It has the same rise of 3, run of 2. BF is completely horizontal. And then I have a couple of dimensions in here. This distance is 2. This one is 1. And if I need it, this one is 3. Okay. Now I want to find the force in BF. So sometimes I can write one equation and solve for it. In this case, I don't see one equation. Like if I write the summation of forces in Y, then I can't even solve for BF. If I write the summation of forces in X, I have 3 unknowns in that equation. If I write a summation of moments, then I can solve for some things, but not BF. So I won't have to write more than one equation. But I have 3 unknowns, 3 equations. I should be able to solve for it, but there's not a single equation to write to solve for it. So how about we do the summation of moments about B? What if we do B? The other option here is I could write all 3 of these equations and solve them simultaneously. Let's do clockwise positive this time. All right, so I am saying that this piece of the truss, this section of the truss, is not rotating at about point B. And so therefore all the moments about point B need to add a 0. So I've got 0.67, this is the reaction at A, so kips. And it has a moment arm of 2 feet. And then FG is at an angle, I could go try to figure out the perpendicular distance here if I wanted to. I'm just going to break FG into X and Y components. So here's FG X, and there's FGY, and use both of those. So FGX would be counterclockwise, so minus, and to create that one, FG, the force in FG, times 2 over 3.6, so that's the basically the cosine of that angle there where the G is sitting. Multiplied times 3 feet. And then GY also goes counterclockwise, so let's see if we can minus FG, the cosine of, or well, not the cosine, the vertical component, the Y component, would be 3 over 3.6. So I'm using the definition of the sine of that angle. It has a moment arm of 1 foot. Oh, geez. All right, all of those moments need to add to 0. BC and BF, their line of action actually goes through point B, so they don't create rotation about point B, so they don't create a moment about point B, so they're not in the equation that I'm here. The only thing in this equation is FG. So I kind of took the same approach of doing summation of moments about a pin to get rid of the two of the unknowns and then solve for the third one. I could have also done the summation of moments about F, even though it's not on the, it's not on my diagram, it's still a point over here. So I could have done the summation of moments about F. That would have eliminated BF and FG, and then I could solve for BC. That'd have been another option. So let's solve this equation and see what we end up with. 0.67 times 2. So there's 1.34 kip feet minus FG times 2 divided by 3.6 times 3. 1.67 minus FG 3 divided by 3.6 times 1. 0.83. So those all add to 0. So I get 1.67 plus 0.83. So I get 2, by moving the FG to the other side of the equal sign, they become positive. So 2.5 FG and 1.34 kip feet. I'm kind of leaving the units off here, but make sure that you keep everything in the same units so that when you divide, they actually work out. So 1.34 divided by 2.5 gives me a positive number, so FG, let's do therefore, FG equals 0.536 kips. So the positive number on this FG means that it's actually going the right direction, so FG should be in tension, and it's 536 pounds. Okay, now I can write summation of forces in the Y direction, I can write summation of forces in the X direction, or I could even write a different moment equation. Let's do a different moment equation just to show that process, that you can, if it's useful, apply a second moment equation. In this case, that will be useful for us. It just does mean that at that point, one of my X or Y equations kind of becomes redundant. I can still only have 3 independent equations when I have a concurrent, or well, not a concurrent, a non-concurrent force system like this. So I can write 2 of them as moment equations, but then if I write also the X equation and the Y equation, one of those is going to be redundant. So I can only have 3 independent equations. And I could write, let's go ahead and write that one that I drew, summation of moments about F equals 0. We'll keep with the clockwise positive idea. And this one will solve for BC for us. So I still have the 0.67 kips from AY. BF, that has, I didn't label it, but if I put this, there's another 2 feet. So it has a moment arm of 5 feet. FG, the resultant FG, not FGX and FGY, but the resultant FG actually goes through point BF, and you can kind of be clued in on the names of the things. I'm summing moments about point F. I am going to eliminate force BF. I'm going to eliminate force FG. So it actually tells you in the name that BF goes through point F, FG goes through point F, so you can be sure that they're not going to actually enter into this moment equation. BC, it is at an angle, so I've got the BCY component. I have BCX, but it's going to be right on top of that BF that I've already drawn, and so it's not going to create a moment about point F, so I won't even draw it because it's getting kind of cluttery on my little diagram here already. So what I would end up with is BCY, and that's going to go around clockwise, so plus. BCY would be the 3 over 3.6, so I'm basically doing the sine of that angle. Oh, and it has a moment arm of 3 feet. In my equations down here, in the moment equations, I don't always keep it consistent, but I try to have the force and then put the distance in parentheses. I try to do that because a lot of times you have, getting to write these really quick and you're looking to multiply 2 things together, a force and a distance. But a lot of times with the force at an angle, the 2 things that you multiply together first are the force and some angle, cosine or sine, and you forget to also multiply by the distance. If your brain kind of locks into this pattern of multiplying 2 things together, that way, this way, if I put the feet or the distance, whatever it is, in parentheses, maybe it kind of combats against this pattern recognition that your brain wants to fall into. All right, so I've got the y component times 3 feet. All of the other forces go through point F, so they're not going to create moments about point F. So these two need to balance. So that's going to say BC equals, it's going to come out negative. So let's see what it is. 0.67 times 5. And then I got to divide that by 3 over 3.6. And then by 3 again, 1.34 kips. And this time the negative sign means that I actually chose the wrong direction for BC. It should be pointing towards the joint B or point B, which means that BC is in compression. So you probably, maybe, I don't know, once you see more of these trusses, you can probably look at the truss and see how member BC is in compression. It might be harder to see how FG is in tension, but you could probably see how BC needs to be in compression with the way it's loaded. But if you have to sit there and well, is it, or you do some mental calculations, to me, it's faster and maybe even more accurate to just draw everything in tension, and then if you get a negative sign in your equation, that, oh, all right, that was compression. But if you're really quick at looking at oh, those are in compression, those are in tension, and whatever, then sure, draw them the right way to begin with. Even if you draw them what you think is the right way and you get it wrong, you guessed wrong, the negative sign, you'll still calculate a negative sign that will tell you guessed wrong. It just won't necessarily mean it's compression. It's just the opposite of whatever you drew. All right. So now there's not a moment equation that's particularly useful to me. I could do moments about G, I suppose, and solve for BF if I wanted to, but how about we just write summation of forces in the x direction? So AY, let's get our stuff here. AY is not in the x direction. AX is 0. I have FGX, which is going to be FG times 2 over 3.6, that's FGX, and I drew it going positive, plus BF, plus BC, which is going to be the same 2 over 3.6, so this is BCX. Those need to add to 0. Now, and I normally like to do it this way, where I go back to the Freebody diagram that I originally drew, use those arrows to write the equation out, and then go plug in the actual values of stuff that I figured out. That's just the way I like to do things though. So FG I figured out is 0.536 kips. So I would have 0.536 kips times 2 over 3.6. I don't know BF, that's what I'm trying to solve for. Plus BC is actually a negative 1.34 times 2 over 3.6. And I'm probably writing out more little details than you need to, but this way you're less likely to make a mistake, although I still do. All right, so 0.298 plus BF minus, because this one has the negative sign on it, 1.34 times 2 divided by 3.6, 0.745 equals 0. Therefore, BF equals, and I move the negative 745 over, it becomes positive, the 298 becomes negative, so it's a net positive of 447, 0.447 kips. So, and I haven't been writing this, but remember, we really should write 0.447 kips, and it came out positive. In my system, that means it's tension. Here, BC, 1.34 kips compression, although we weren't actually trying to solve for that one. And this is tension. Now, that actually took us quite a while to solve, you know, because we're going through every little step in detail. This exact problem might have been one that's on the border between, is it faster to go do joints at A and then one of these others? But let's go back to the original thing. If I wanted to do joints at A, that'd be fine. I'd find AB and AG, or at least AB. But then I could not immediately go to joint B because there's still 3 other unknowns. So I'd have to go to joint A, figure out what BG is, then go back to joint B and solve for BF. So this particular arrangement of the truss and the member I'm asking for the force in is one that method of sections might be a little bit faster. Method of joints is not far behind, but there could be other examples where maybe it's even much faster to solve for the force if it's method of sections. CF in here is one that's, you might think, oh, I'll do method of sections on that one, but it has a problem for method of sections anyway. So if I wanted to do this guy, then there's not a way for me to draw a section, right? I can draw this, but that's just method of joints at C, right? But if I do like this, then the section has 4 unknowns in it, so that doesn't do any good. If I do like this, then again I've got 4 unknowns in the section. In either one of the sections, they're going to have 4 unknowns. So sometimes there's not a good way to get to one of these forces on the interior part of a truss with method of sections, but it does. On an exam, how this will show up is you'll be presented a truss problem, so something like this, and it'll ask you to solve for a member force or the stress in a member, which means you have to find the member force. And then it's not going to be said, use method of sections, use method of joints to solve for this. So it's going to be up to you to look at it and say, oh, this one will be much easier to solve if I do method of whatever. Yep. Yeah, so that's what I was going to say. This particular one, if I was trying to solve for member CF, what I would do is I would do the section we just did, solve for BC, which we did. We actually did that second. We could have done that first, though, by doing moments at F. And then I know BC, and then I do go up here, and I draw a joint at C and solve for CF. So it's totally fine to, for a while, do method of sections, get some information, then look at the truss and say, oh, now I can do method of joints at that point. Or the opposite, do a method of joints, and then you have enough information to do method of sections. It's probably normally going to work the other direction, do method of sections first and then do method of joints, but not guaranteed that that's going to always be true. But it's totally fine to switch between the two. On exams, they're kind of set up to where if you do method of sections at this particular section, that leads you straight to the answer. If you do method of joints, that leads you straight to the answer. They're not going to be set up to be tricky like this one. There is one I wanted to bring up in web work. If I can find it, get my mouse to go. Let's see. There we go. Web work. See if I can find. Oh, gotta log in again. Homework sets. Let's stop acting. Maybe in 7. No. Basically, when it looks like this, probably method of sections. Although in web work, there are some where it's like solve for every piece. So don't wait. There's plenty of practice to be had. I'm not finding the one I want though. These are just moments. Oh, now that I pulled this one up, we haven't specifically talked about pulleys and ropes and things like that. There's no trick to these things, but basically just draw the Freebody diagram, and these are all frictionless. Even if it doesn't say the word frictionless, they're all frictionless. So the tension in the rope never changes, it just changes direction. So anywhere you cut that rope open, you see F rope pointing in tension away from the rope, away from the Freebody diagram. Still not the one I was looking for though. Maybe it's not in here anymore. Actually, this is probably one we need to look at a little bit. This is not a truss, by the way, but let's actually divert from trusses for a second, because this one is something that we probably should describe what's going on. Oh, my number lock is on. Yeah. The blue one. Oh, the pulley one. Okay. Yeah. Now, what about the pulley? This pulley? The first one. Okay. The easy pulley. All right. Let's do the easy one first. This one.
This one not given a angle, not given any distances, all the gears like technically isn't force their hump just 1.5 kip.
The force in the rope will always be the same. This is saying the force in the hook. Maybe this is a good one. Let's do this. Let's copy that. And let's go back over here and look what's happening. Don't need all of this. Make it bigger too. All right. So I don't even know what the number was, 1,500 maybe for mine. Yeah, 1,500 pounds is what's being lifted here. So F hook is 1,500 pounds. So what you do with these things is all about drawing the free body diagram as long as the pulleys are frictionless, which ours are. Once the pulleys start to have friction associated with them, then it's a little bit more complicated, but we're going to only deal with frictionless pulleys here. So you know one thing, you know 1,500 pounds, and I guess technically you know the arrangement of the pulleys and the ropes and everything. And we're assuming that the rope doesn't stretch, it doesn't do anything. The force in the rope is constant. So the tension in the rope is constant anywhere in the rope. So what you do is you draw a free body diagram like this. And let's do that. Let's paste it again. Get rid of all of that. Make it bigger. And let's draw the free body diagram this way by basically covering up everything else. All right. So we're going to cut all of this stuff off down to there. And everywhere I cut the rope open, every one of those is the force in the rope. Every one. So 1, 2, 3, 4, 5, 6, 7. So we might even put times 7 instead of writing force in the rope 7 times. And then I just do, okay, summation of forces in the y direction. I'm assuming that, you know, kind of x is this way, y is that way, equals 0 because it's in equilibrium. And I have 7 forces in the rope going up and 1 force in the hook going down. Those have to add to 0 or else it's moving up or down. And I know that the force in the hook is 1,500 pounds. So force in the rope equals the force in the hook divided by 7, which is 1,500 pounds over 7, whatever that number is. So they're actually pretty straightforward. The other pulley cable or pulley problem is the harder one just because you've got angles to deal with. In this one, there is an angle, the force in the rope over here at coming off of pulley G, but it doesn't matter what direction it's going. It doesn't matter, right. In the other one, it matters because of some of the things you need to do to solve the problem. If I needed to solve for like the resultant force on G, you know, what angle is that resultant at, then it matters. But I'm not interested in what the result, you know, there's some resultant force here going some direction, and I'm not interested in what's going on there, so that's why the angle doesn't matter. In the real world, the angle matters because the rope wraps more around the pulley, depending on, or more or less, depending on which angle you pull the rope at. And that amount of wrap affects the friction, right? Because there's more or less rope around the pulley. And so that does start to matter in the real world, but in the frictionless world that we're living in, it doesn't matter. So it's all about drawing free body diagrams and recognizing that the force in a continuous rope doesn't change. Now, this other problem, it might be multiple cables. I can't remember. Let's see. That's not it. Nope. No, this is one continuous cable that goes all the way around. So this one, you've got to do some free body diagram work on this cross-shaped piece. And in that case, you do need to know those angles. Or maybe you're trying to solve for those angles even. No, they're given. So that one, the angle is important because you have to write a concurrent force system that uses that angle to get anywhere. Let's see if I can find, that one. I did this guy. Let's copy, I don't need to save it. Copy that. This one, oh, okay, can't do that. Fine, we'll just do this. All right, let's make it larger to see things. So this one is 3D and it's talking about moments. So that's where it is something we haven't really talked about yet. There we go. All right, we need those to get our numbers going. All right, what it's talking about is, oh, well, let's go read the problem statement. I've got this tube that's been around, it's about bolted to the wall with these brackets at A or at B, C, and D, and I want to find moment vector components that this force F, which is kind of down in towards the wall and towards us, I guess, is creating about these different points. So I've got this grid down here, 3 different points, point B, C, and D, and then the moment about the x-axis for point B, the y-axis, and the z-axis for point B. That last column is the result. So it's basically the square root of the summation of the squares of those moments is all that last column is. So for this moment, point B, moment at x, what I'm talking about is point B here. The x-axis is shown. You have to use the axis, at least the orientation. You can move the x-axis around, but they have to use that orientation. So I would be talking about this axis. There's the x-axis. So point B, mx, so the moment about the x-axis that I've drawn, kind of the second one there. So this force has 3 components. It has one component that's going, I'm going to do my best here. This is Fx. This force is like I'm pulling in the x direction at point A, kind of pulling towards myself. That would cause the pipe length AB, is all I'm looking at right now. So the length of pipe AB, it would cause it to want to rotate, but it doesn't cause it to want to rotate about the x-axis. It's causing it to want to rotate about the z-axis. This force also has this component, Fz. If I ignore the other forces, directions, you know, the x and y components, at point A I'm pulling straight down. That does want to create a rotation of length AB about the x-axis at B. So I would take this force Fz, I have to figure out what that is, times what is labeled here as D. That's going to create a rotation about point B. Now this problem says, let's see, moments. Report the sign of your answers according to the right-handed sign convention and the coordinate axis shown. So that literally means take your right hand and curl your fingers in the direction from x to y or y to z or x to, well, z to x. Basically, so the coordinates shown down in the lower left, if I curl my fingers in the direction of y to z and my thumb points up, right, that's in the positive z direction. So the rotation is the curling of the fingers. Here, I would have to basically think of my wrist at point B, curl my fingers in the way that Fz is wanting to rotate bar AB. That's a lot of letters, but it would go like this direction, and my thumb would be pointing in the opposite of the positive x direction. Basically, my thumb would have to point in the direction of BC for my fingers to be able to curl downwards the way that Fz is wanting to pull bar AB. So bar AB wants to go this way, right? Kind of, sort of, if you interpret that drawing the right way. In fact, it's kind of looking hard to read. Let's see, how would be?
Would you mind explaining that again?
I don't mind it, no. I can't say any other words though. So the idea is so what I'm trying to, first of all, I'm trying to figure out, do I put a plus sign or a minus sign? That's what I want to know. Is this a positive moment or a negative moment? I have already established down here in the bottom left corner what is positive x, positive y, and positive z. So that's just given to me. So I have to figure out, does this moment, the one that I drew here, the red curved arrow, is that positive or negative? That arrow represents what force Z, let's erase this one. So force Z pulling down at A would want to make AB go in that direction. It's going to go downwards towards the bottom of the wall, kind of. So it's going to want to pull it down. So I simplified that by drawing this curved arrow at point B. That's the way that bar AB wants to rotate if I pull where FZ is located, the force in Z direction. Then, how to figure out if it's positive or negative, the problem told me to use basically the right-hand rule. So use the right-hand rule. So you take the fingers on your right hand, you have to use your right hand, the fingers on your right hand and make them curl in the direction that this arrow is going. So curl this way. And when I do that, my thumb has to point in the direction of BC. So it has to point, my thumb has to point that way. That arrow, this arrow, is in the opposite of the positive X direction. So this would have to have a negative sign on it. I'm not sure I could draw a picture of a hand here. Let's see. You got thumbs going this way and your fingers are going this way. Well, so that's more like the vector notation, in which case that is the right-hand rule. This one is related to that, but yeah, what you're talking about is your pointer finger is the x-axis, or in this case, you're talking about the y and z plane. So your fingers would be the pointer is the y-axis, middle finger is the z-axis, and the thumb is in the positive x direction. That's how you work it out as vectors. Here we're just talking about the direction of the moment. So if you can do the vector orientation thing, basically it's the same idea, yes. Here I'm just making it simpler, where you just curl your fingers in the direction that this, basically grab bar BC, grab at BC and rotate it in the direction that FZ is going to rotate. Whichever way you have to turn, curls your fingers in, or your wrist, whatever you want to think of, in one direction. If your thumb is pointed in this direction, if your thumb is pointed in this direction, that lines up with the positive x direction that's defined by the coordinate system, and you get a positive moment. If it lines up in this direction, that lines up, if your thumb lines up in that direction, that is the opposite of what is defined to be positive x. So it creates a negative moment. It might be useful to physically get a paper clip and make that thing, and I have to twist it this way, I have to twist it that way. And it's always, which way is your thumb pointing when you have to twist it in these certain directions. Your thumb lines up, if it lines up with one of your coordinate x, y, or z axes, then it's positive. If your thumb is opposing that, the other direction, then it's a negative moment.
We're trying to find if z is positive.
If I'm trying to figure out if this term, this is a moment, this is the moment created by only the z component right now, fz, about point B. So that fz times d, the distance between point A and B on my picture, if that is positive or negative. Moment about the x-axis. Yeah. So the rotation occurs about the x-axis. The vector of the moment. Yes. There is one more component here. There is also, we did z, we didn't do x. No, we didn't do y. So there is a tiny little fx component here. Fortunately, that one points right to point B, so it does not create any rotation at all, and it wouldn't create rotation in the x, about the x-axis anyway, so at point B. So you do this for every force component at every one of these points. And that's what the little chart here is wanting you to fill in. So in our chart, we would fill in moment in about the x-axis for point B would just be the z component of my force times dimension d, which is 77 inches on mine. So let's see if we do that. The force in the z component. So F, or the length of F, let's do that, is equal to the square root of, it's actually called a squared plus b squared plus c squared on my diagram. So the length of this vector is, A for me is 14, B for me is 22, and C is 20. The square root of all of that is 32.86. These are all inches, so inches. And then FZ is C over the length of F times F. Oh, I don't know what F is. Let's see. F for me is 100 pounds. He's given in the problem statement. So filling those in, C is 20 inches. So here I'm just trying to get the, kind of like when we did the 3D concurrent force systems, I'm just trying to get the component in the Z direction in this case. So this is basically the cosine of theta Z for the force F. (20 divided by 32.86 times 100 is 5. That doesn't seem quite right. That's not right. 20 divided by 32.86 times 100. 60, that's better. All right, 60.86 pounds. And then if I multiply D in my little chart is 77 inches. So FZ times D equals 60.86 pounds times 77 inches, 4,686.549 inch pounds. And it is going to have a negative sense compared to the coordinate system that they gave me. Let's see if that's all right. I guess it doesn't matter what units I use here. So what's my number? Negative 4,686.549 inch pounds. I don't know if it likes pound force or pound. Don't know. Let's see. Show me. Oh, it did like it. All right. So, and we were reasonably close. We did round a little bit differently. We mainly rounding in this one occurred when I made this number right here, the length of force F vector, because I did round that a little bit. And so you go through and do that with every one of those, and it's mainly trying to, can you wrap your mind around how to create this little force? And chances are you could go in and just, we'll try the positive sign. But you do need to figure out how to make the force or the sense of the moment positive or negative using this right-hand method. I can't guarantee, but sometimes on exam 1, a problem like this shows up and you'll have half the answer is positive, half the answer is negative. You get partial credit if you choose the wrong sense, but the correct magnitude.
So it's negative because it's, I guess, compressive?
And in this case, the moments aren't compressive or tensile. It's negative because of the direction it's rotating. Yeah, we'll look at later how moments create tension and compression at the same time in a beam. So they're not thought of as tension and compression. It's, is it rotating clockwise or counterclockwise about this axis? And maybe that's an easier way to think about it. In this example, if you can visualize the rotation about the z-axis, so meaning using the z-axis as your center, and are you rotating around it one way or the other way? In this way, if you're rotating around it clockwise, then that is a negative moment. That's what the right-hand rule is telling you for this. And if the part AB is going around counterclockwise, then that's a positive moment. And that should hold true for all of these things. You just have to look. Imagine you're looking down the axis. So, you know, your eye is over here, and you're looking down the axis. Then, let's draw a little person. Then clockwise moments are going to be negative in this problem, and counterclockwise moments are going to be positive. That's the other way to look at it without the hand thing going on.
Okay, so it says the force is going this way.
Yeah, the force is going towards the wall, down, and out towards you, all at once.
Going like kind of like this?
Yes,
like
from your point of view, yes.
Here. Okay, because I think that's what was kind of confusing me, because I thought the force was coming this way, so I thought it would be rotating like a different way.
Well, it is rotating in other directions. We're talking only about the x-axis for this one little blank in the problem. So that's another part of how it's being parted out. We're only talking about what rotation occurs about the x-axis for this one little blank. And then it is rotating about y and z also, but they're in these other blanks. And once I figure out this top row of blanks, then I can square them all, add them up, take the square root, and figure out the net moment about point B. So I think you're thinking correctly. You're just doing it all at once, and the problem is asking you to do one little piece at a time. All right. Anything else? All right. Let's say that we're good for now.